Hello everybody, welcome to our webinar. I'm going to present you two case studies in which major soil threats will be targeted and evaluated: soil pollution and soil erosion. I'm going to share my screen. Sorry, I have problem with sharing my screen.
Professor, good morning.
Good morning.
Hello. Is there any problem?
I cannot share my screen.
It would be better to upload the presentation, not to have a share screen, to have a better quality in the sound.
I uploaded my presentation.
We cannot see the presentation. We only see your screen. Stop the screen sharing.
Okay, now we are ready to start. As I told you, I will present you two case studies which are dealing with soil pollution and soil erosion. Soil is defined as one of the fine earth which covers land surfaces as a result of in situ weathering of rock materials or the accumulation of mineral matter transported by water, wind, or ice. The distinctive feature of a soil is that to this weathered mineral is added organic material. First, soils are built up of different horizons. Surface horizons are usually characterized by accumulations of organic materials resulting from the addition of plant and animal residues. They are designated as A horizons. Another horizon is the B horizon, which encounters the maximum intensity of weathering and transformation and may also exhibit the accumulation of materials translocated from surface layers, such as clays, organic matter, iron, and aluminium oxides. The lowest horizon is the C horizon, which is situated below the B and represents a layer of relatively unaltered material from which the A and B horizons may be developed. So we are talking first about the soil pollution. Soil is the world's largest filter, which protects the environment by keeping water and air clean in different environments. Also, soil can hold contaminants and immobilize them, reducing groundwater pollutants. The main sources of anthropogenic pollution are chemicals, which are used or produced as a byproducts of industrial activities, as well as domestic, livestock, and municipal wastes, agrochemicals, and petroleum-derived products. Soil pollution also severely degrades the major ecosystem services provided by soil. Soil pollution also reduces food security by reducing crop yields due to toxic levels of contaminants and by causing crops produced from polluted soils to be unsafe and consumption by animals and humans. Heavy metals are the most persistent and complex kind of pollutants to remediate in nature. Among the heavy metals, zinc, nickel, copper are relatively more toxic to plants, while arsenic, cadmium, lead, and chromium are relatively more toxic to higher animals. Common practice in risk assessment of metal contamination is to compare the present concentrations with so-called critical concentrations at which adverse effects could be expected. The presence of strongly magnetic fraction of iron oxides in the anthropogenic emissions causes a subsequent extra enhancement of the magnetic soil signature on the surface of the polluted media. This signature is registered by using fast magnetic susceptibility measurements. These measurements may be done in situ in the field or using soil samples in the laboratory. Depending on the iron availability in the waste products, different degrees of magnetic enhancement are observed in the contaminated soils. In order to understand the principle behind the magnetometry method used to evaluate the soil pollution, we need to know what is the magnetic property, magnetic susceptibility. Magnetic susceptibility is measure of the magnetic response of the material to an external weak magnetic field. You see the expression here, where the K is the volume magnetic susceptibility, while K is the mass-specific magnetic susceptibility, which is calculated afterwards. Now we are going to start our discussion on the first case study, which I'm presenting to you. The aim is to perform site assessment for the presence of soil contamination in an area of lignite burning power plant complex called Schwarze Pumpe in Saxony in eastern Germany. The outcome of this exercise will be to characterize the natural and anthropogenic factors of the case study area with emphasis on geology, soil types, and magnetic susceptibility data. And then the second, we will get information how the results of field measurements of magnetic susceptibility are analyzed and interpreted. The first step in such investigation is to gather information about the site, its geographical position and state of environment according to the published previous studies. The study area, in this case, is marked on the map, and it's a border region shared by Germany, Poland, and Czech Republic. And this area is long characterized by extremely high values of pollution. During decades, industrially produced air pollutants, especially sulfur dioxide, water pollution, acid rain, and other effects affected severely the health of local residents and the surrounding environment. This study area is part of I'm going to show you also the geology and soils in the region. So this area is part of marine intercontinental Bohemian Cretaceous basin in Central Europe. It is characterized by quite high thickness. The hemipelagic marls and limestones are present in the northwestern part. Second part of the Bohemian Cretaceous basin in Saxony is represented in the area of Zittau Mountains by fine-grained sediments. Exploring the soil map of Germany, we see that the study area, which is here in this region, is characterized by the presence of several soil types as cambisols, podzols, glaze soils, and stagnosols. Another important information which is necessary to obtain is related to the main industrial activities and the sources of pollution and loads. Saxony has large natural ore mineral deposits, giving its name to the ore mountains. For hundreds of years, mining, ore processing, and smelting dominated the landscape and society in the ore mountains. Therefore, many areas show high concentrations of arsenic and heavy metals in soil, strongly increased by mining and industrial processing, which lasted for several centuries. The main anthropogenic inputs are atmospheric deposition from mining, ore processing and smelting, as well as traffic, which is a source of lead, pesticides and fertilizers as a source of copper, and atmospheric deposition from various sources. High concentrations of heavy metals are also found in the floodplains of rivers with catchment areas in this region. Currently, lignite is the only major industrial resource still mined in significant quantities. On the next slide, I have shown the sampling locations for doing magnetic susceptibility mapping. This is the first step in any magnetometric study. In this specific case, which we discuss here, volume-specific magnetic susceptibility was measured at 180 locations of topsoils. These measurements were done using Partington surface loop sensor. Multiple readings have been taken at each site within an area of about 4 square meters in order to check for spatial homogeneity and to determine a median value. Red dots represent also the locations from which vertical cores were taken and susceptibility was measured along a depth of 50 centimeters. So up to now, we had accomplished the stage 1 objective, which is to characterize the natural and anthropogenic factors at the case study area. And we had learned what are the main rock formations in the study area, what are the soil types in the study area, and what are the main sources of anthropogenic pollution. The next step is to define the stage 2 objective, how to make an informed choice of topsoil sample locations in order to perform laboratory analysis of the content of contaminants in this anthropogenically polluted area. The necessary tasks are to interpret the results from topsoil susceptibility mapping and to suggest suitable sampling design for taking samples for chemical analysis based on the results from initial magnetic susceptibility screening. Here we start with the examination of the depth variations of magnetic susceptibility, which was measured along the vertical course. We defined the background value, which is the minimum values observed along the sediment course, and the area below the vertical distribution curve, which is this, minus the background contribution, provides a measure of the total amount of pollution-related magnetic concentration. In some sampling points, different susceptibility curves were obtained with two maxima, which are probably related to dumping of waste material in the older times. Here on this slide, you see the spatial map of field measured magnetic susceptibility. This map is usually prepared by Krajcik interpolation. The first panel represents the map of raw field measurements, while the second map represents the signal after subtraction of background values, which are estimated from the vertical course. And this is the estimated background signal in this area. Now, the major task in the study comprises stage 2. We should perform evaluation of the efficiency of magnetometric methods by comparing the maps of heavy metal pollution obtained by an informed initial decision-making using magnetic susceptibility map with maps obtained using random choice. The aim is to learn how to choose the locations for soil sampling by using field map of magnetic susceptibility. For that purpose, we use the map of the corrected for background values map of magnetic susceptibilities, and we need to have the right choice of the sampling points for laboratory analysis of heavy metals. So here is the right choice of the sampling sites. Having in mind that laboratory analysis of the contents of heavy metals are quite expensive, labor and time consuming, we need to define an optimal set of points such that to pick the main maxima, minima, and plan higher sampling density around the local maximum. These points are marked by star symbol here on the map. Let's consider as a true pollution map the map which is obtained from all taken 85 vertical cores from the area, which have been chosen after the initial screening of topsoil magnetic susceptibility spatial map. And now the map of the heavy metals content, which is obtained using susceptibility map of as a guiding tool. This is the true map of the heavy metals contamination. It is represented by the so-called pollution load index, PLI, which is calculated by a formula suggested by Tomlinson, and includes the contribution from all the chemical elements included in the analysis of the chemical composition of the soil samples. Here we compare the obtained map of the true pollution with another maps which are constructed by data obtained after random sampling locations within the study area. Each of them picks only part of the true picture, which results in some parts of the area in incorrect estimates of soil pollution, and some of them even cannot pick the major maxima which should be detected in the study area. From this result, it's clear that the geochemical map obtained from the 30 sites targeted by the magnetic pre-screening reveals the essential features of the true pollution map, which is based on chemical analysis. As a conclusion, we may say that this case study demonstrates an approach where sample selection criteria derived using initial magnetic susceptibility screening and core sampling were systematically used to influence the planning of detailed site investigations for the purpose of risk management decisions. The study demonstrates that using pre-screening of the target area using magnetometric method is extremely useful for detailed, cost-effective and evidence-based approach in evaluation of spatial extent of anthropogenic pollution of soils. This information allows maximum decrease of assessment costs, along with precise delineation of all critical locations, potentially having high contamination level. The same approach is valuable too also in monitoring the progress of long-term remediation measures. The second case study, which I'm going to present to you in this webinar, is related to estimation of soil erosion on sloping agricultural lands in the middle mountains of Nepal. First of all, what is soil erosion? The upper layer of the soil consists of fine soil particles. It is rich in minerals as well as humic substances. Sometimes heavy rain, running water, and wind remove the top layer of soil, and this phenomenon is called soil erosion. Water erosion starts when raindrops strike bare soil and mix it up into flowing mud. The muddy water tries to soak down through the natural cracks in the soil, but cannot do so because the mud seals the cracks. Mass movement is an erosional process that moves rocks and sediments downslope due to the force of gravity. The material is transported from higher elevations to lower elevations, where other transporting agents, like streams or glaciers, can pick it up and move to even lower elevations. Another type of erosion is wind erosion. It's also a natural process that moves soil from one location to another by wind power. This erosion can cause significant economic and environmental damage. Wind erosion can be caused by a light wind that throws soil particles along the surface through a strong wind that lifts a large volume of soil particles into the air and creates the storms. While wind erosion is most common in deserts and coastal sand dunes and beaches, certain land conditions will cause wind erosion in agricultural areas. Soil erosion by wind and water is the most damaging and widely spread form of land degradation, which accounts for 83% of the global land under degradation. What will be the case-specific learning outcomes from this study case? First, we will characterize the soil quality of sloping agricultural lands in Nepal. And second, we will learn about the erosion processes. And finally, we will assess the major causes of soil erosion on sloping agricultural lands in Nepal. The major variables which are affecting soil and its erosion are climate, soil, vegetation, and topography. Of this, vegetation and to some extent soil and topography may be controlled, but the climatic factors are beyond the power of human being to control. Thus, we need to consider the environment at the study site. The Himalayas mountain ranges are known, except as with the highest peak on Earth, also as suffering from deforestation, soil erosion, and downstream flooding. It's estimated that about 45% of the total land area of Nepal is affected by water erosion, and erosion rates are estimated to be as high as 50 tons per hectare per year. This topsoil loss through surface erosion and subsequent decline in soil fertility is a concern for both sustainable agriculture and food security. There are three theories for the causes of these issues. First, that the human activity is the main cause of land degradation. Second, that the natural processes outweigh the importance of human impact. And the third one is that the land degradation is a product of both natural and social forces. The study site is located at the Jinghu-Kola watershed, which is located 35 kilometers east of Kathmandu in the middle mountains of Nepal. Climatic conditions there are favorable for crop production, but the rainfall occurs generally during the 4 months of the monsoon season, and topography in the area is characterized by elevation from 790 to 2020 meters above sea level. Steep side slopes result in a high erosive potential, while the flat valley bottom acts as a sediment depository. The soils in the watershed are broadly classified into red and non-red soils, with red soils comprising 37% of the watershed. The red soils are formed on quartz-rich phyllites. They are slightly weathered, acidic, and having high iron and aluminum content, high clay content, which is dominated by kaolinite. The non-red soils are called alphisols, and they are formed on schist, quartzite, sandstone, and siltstone. The main land uses in the watershed are represented by irrigated agriculture at level terraces, rainfed agriculture on sloping terraces with no provision for irrigation. There are forests with ground density more than 10%, and also rangeland utilized dominantly for grazing. This is more information which is not so important, and now we had reached the objective of the first stage, namely the identification of the factors which control soil erosion in general and water erosion in particular. The questions which we answered can be summarized as: what are the main factors which control water erosion? What are the soil properties affecting water erosion, and when the highest erosion rates are expected to occur in a monsoon climate? And now we are going to move to the second stage, when we will assess the erosion plot data and investigate potential factors which contribute to spatial and temporal variability in soil loss. Different methods have been used to study soil erosion by water, which include erosion plots, erosion pins, tracers, and stream sediment monitoring. Erosion plots in the field usually consist of small plots delineated with plastic or metal sheets, a collection tanks on the bottom of the plot with the volume of sediment and water determined after every storm event. The erosion rates in Nepal have increased since 1980s, although the rainfall did not. This is visible from the figure on the right and can be explained in the context of climate change, since the number of rainy days is decreasing, but the rainfall volume is not changing. Therefore, the same amount of rain is falling with greater intensity, which leads to stronger and stronger erosion during the monsoon season. In the case which is presented here, 5 plots have been established. Each contains 2 terraces connected with a steep terrace riser. The cropping practice in all plots was the same. This was the cropping of maize during the rainy season and either millet or wheat during the dry season. All plots were on non-red soils, and erosion and runoff were measured at event basis after each rainy event. And this is accomplished by the following procedure. The 3 drums were located in series at the outlet of each plot. After each erosion causing storm event, the total height of water and sediment in each drum was measured, and water and sediment samples were taken. Using these measurements and the known dimensions of the drums, total erosion and runoff were calculated for each storm event. In addition to monitoring erosion on upland plots, also sediment accumulation on lowland rice fields was determined using accumulation pins. Some picture is shown here, and these are the pins. These pins indicate a change in soil level at each specific location. Between 4 and 12 pins were installed in each individual field, and the soil height relative to a notch showing the original soil level was measured before the pre-monsoon and after the monsoon season. Data which is presented in these tables show that we have different erosion and accumulation estimates, erosion on the sloping land and accumulation on the lowlands. Overall, average of sediment accumulation is estimated as being 6.6 millimeter per year, while the overall average of the annual rate of soil loss was estimated as 26 tons per hectare per year. Looking in details in the study area, some locations experienced much higher soil losses, even during relatively weak monsoons, than those in the JiC Kola. This is because of different reasons. For example, one of these reasons are that some lithologists, such as phyllites, develop finer textured soils, which are more susceptible to erosion. Another reason is that there can be terrace slopes of much higher angle, which also accelerates erosion, or we have areas which receive substantially more rainfall than others, and this is a very local phenomenon. High soil losses are estimated on steeply outward sloping unditched red soil terraces in this study area, with soil losses up to 20 tons per hectare. What we had learned from this case study, it demonstrated how erosion estimates are done using traditional field scale approach. Moreover, it shows how the erosion rate depends on the properties of the watershed, and also gave information on the accomplishment of field erosion studies. And this is the end of my presentation. I hope that this was useful and good example of the application of different methods for evaluation of soil quality.
Okay, then we can call an end in this session.
Okay.
Thank you very much, Professor.
Thank you.